Yes,
Well,
thank you.
sorry for the small delay. Okay, so Jaron is here, so he's ready to talk, so we'll start. Thanks.
Thank you for the introduction. My name is Jaron. I'm going to talk today about geometry and descent in random landscapes. Before I begin in the content of the talk, I have a quick outline of what I'll discuss so you can follow where we are, perhaps, in the progress. First, I'm going to introduce quickly complex landscapes, why they're interesting, what sort of systems we expect them to be able to describe. And then I'm going to focus in on the specific mean field models that we can actually study analytically very well. I'll introduce those models. Then I'll explain how we can characterize the geometry of the energy or cost landscape in these models using statistics of stationary points, minima, maxima, saddle points in the function. Then I'm going to explain some old results, ancient history, that demonstrate how this kind of analysis of stationary point statistics can succeed very well in explaining in a kind of satisfactory algorithm-dependent way, physics-dependent way, why certain dynamics happens in a subset of these models, the very simplest ones. But then we'll see some recent discoveries, not by me, which show that, in fact, this beautiful correspondence between geometry and dynamics doesn't hold in slightly more complicated models. And so a lot of the motivation then for the next part of the talk will be delving in more deeply to the geometry of these models to look for features that we may hope to use to bridge this gap in these more complicated systems. So I'll explain some work I did in these geometric studies of these more complicated models, which, as a spoiler, don't actually succeed at explaining everything about the gap between geometry and dynamics. And finally, I'll explain some directions for future work, which are inspired, I hope, by what you will see in the talk. So to get started, what is a complex landscape? Well, a complex landscape is simply some sort of function of very many variables, which happens to have very many stationary points, so very many minima, very many metastable states. And a lot of systems that are interesting in physics and other fields are thought to be described by such things. For instance, the energy of structural and spin glasses is very much thought to be described by such functions, but also the energy of other systems, like proteins folding. Fitness in biological evolution is increasingly being modeled with complex landscapes. Likewise, the cost function in machine learning models, which of course we know what the function is, are often complex, which is similar to likelihood in statistical inference. Now, in a lot of these models, we have an intuitive understanding, right, that shared behavior in various systems, like very slow dynamics, aging behavior, this sort of thing, is explained by shared structure in the landscape. We think, okay, you have a complex landscape, you have all these metastable states, it's causing these behaviors to happen. But a quantitative correspondence between the presence of certain features and the, for instance, asymptotic behavior of dynamics like gradient descent or quenches is not actually well understood in most systems. And so that's what we're going to try to look at here. So, for instance, you can look at this landscape. It's a very beautiful landscape. It's not a complex landscape in the sense that I talk, because it's not high-dimensional, but it has a lot of maxima. And you might imagine that you try to run some algorithm to find the highest peaks in this nice picture. And this is a different landscape, which is similar. It has lots of high peaks and lots of low peaks. And you might imagine it looks qualitatively different from the first landscape in a lot of ways. And you can easily think that different algorithms will behave quite differently on these two landscapes. And so a question that we want to try to answer using geometric aspects of these things is what fundamental pieces of the landscape itself drive dynamics to behave in different ways on these different landscapes. So the simple models I'll talk about are not topographical landscapes like the pictures I showed you. They are simple models originally of spin glasses, known as the spherical models, and spherical spin glasses. And these you can think of as defined by a class of random functions, h, that are centered Gaussians, so the average 0, and whose covariance between the value of the energy at two different points on the sphere, so the configuration space is the sphere, I skipped that part, a high-dimensional sphere. The covariance function between the energy at two different points on the sphere is simply given by some function of the overlap or scalar product between those 2 points. So if you give me such a function, you have a model. And the class of models parameterized by choices of the function f is quite broad. In fact, it encompasses every isotropic Gaussian random field on the sphere. So it's a very broad class of models. And these are important in a lot of disciplines, for instance, both in spin glass and glass physics, and also in statistical inference, where the so-called spiked tensor or tensor denoising problem resembles this setup quite closely. Now, in this talk, I'm going to focus on two different subset of this broad class of models. First, the so-called pure p-spin models, which are the most studied of this family of models, which have a covariance which looks like a homogeneous polynomial in, with a degree p, and the so-called mixed p plus s models, where you just have two homogeneous polynomials summed together, which we'll see already just from this very small subclass of these models. There's a lot of richness and interesting behavior that can arise. Yes? Yes, real functions. I did do some studies of complex versions of this, but not in this talk. Only real. It's an energy function. You can think of it as an energy function. Sometimes, if I want to sell something to someone who's studying machine learning, I'll say it's a cost function, or something like that, an objective function. But it's an energy function. H is a Hamiltonian. It's meant to be evocative. So, lots of old work on these simplest possible models, the pure p-spin models, the homogeneous covariance, had discovered some interesting facts about their dynamics. Namely that if you take one of these models and you cool it, say, with slowly decreasing temperature, you find that the energy of your system decays towards a characteristic value at which it gets stuck. Even if you cool to lower temperatures, you never find it go lower in any sort of normal computer or experimental time. And it doesn't matter what sort of dynamics you do in these models. You can also quench quickly. You can anneal as much as you like. You're going to find that once you go under a certain temperature, you always find that the energy approaches the same so-called threshold level. And it's not just true of physical dynamics. You can try very fancy algorithms. Recently, there's been a lot of attention from mathematicians interested in statistical inference who have developed very fancy algorithms for these models, and they've proven that, in fact, that this energy is the lowest you can go, even though it's somewhat far from the ground state. So a natural question to ask, given these facts, is what's special about this energy? What happens in the energy function, these random functions we're drawing from this distribution, which causes this behavior to happen? And there's an old answer, which I'm going to try to inspire by this nice picture here. You have a question, Dario?
This energy that you find is essentially, just to understand the picture, is essentially a point in the landscape that is described by this H function, right?
So this is a quenched problem, right? So you pick a function h drawn from this distribution, which has many, 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 many points all over the landscape.
Okay.
And you try to do gradient descent or something,
Exactly.
say, zero temperature quench, and eventually it stops. You find some minimum.
Right.
And the point is, on average, that minimum, and more than on average at the limit of large n, because it concentrates quite well, you will find an energy density of that minimum that has a certain value.
Okay, and you know that that is not the ground state energy because you have access, you have an analytical way to find the ground state energy.
With these very simple models, we have an analytic way to do a lot. So indeed, we know we can predict very well where the ground state energy should be.
I have a question. Is this an artifact of the infinite range model?
Yes, these are all, so these are these functions defined by these covariances on the sphere, indeed can be realized in a computer or something by all-to-all connections by tensors that have Gaussian IID variables in them. So it is an infinite range model, fully connected.
But what if you change the architecture of your interactions so that they are not all equally strong?
You don't even need to do this. If you simply change the covariance function to a more generic form, like I'll do later in the talk, you already don't see this behavior. But this is skipping ahead a little bit.
Okay.
Yeah. So this is this behavior where every single possible procedure brings you to the same energy is extremely non-generic. It's very specific to these homogeneous polynomial covariance for the pure p-spin models.
Okay.
So what kind of structure might we expect to find at an energy level that has these properties? Well, I'm going to steal this picture from an old paper of a nice energy landscape with lots of minima and maxima, which are easier to see if I color them. Oh, it still looks nice. Okay. If I color them by level, there are high, bright maxima and low, dark minima. I shouldn't use this. They can't see online. And to motivate what level might be the interesting one for dynamics, we're going to fill the entire landscape with water. You know, there's a nice gray sea covering everything, and slowly descend the level of the water. You can see we have nice isolated islands around the maxima, which eventually merge, leaving little pools around the minima until everything is gone. And this process of going from dropping the water level, you might have noticed that the transition from isolated islands to isolated pools happened basically in one level set. If we go back and forth, you can see that, in fact, you know, we have, oh, sorry, that's skipping ahead. Mostly gray and mostly white. And this special level set, if we highlight it, it does the thing which we were describing. It basically percolates over the entire landscape. The whole configuration space is covered by this kind of big percolating structure associated with this level set. But there's also something else which is very nice about it, which is that you can notice that it contains most of the saddle points in this landscape. The saddle points are denoted by these X's, you know, between the minima or between the maxima. And almost all of them are contained in this percolating level set. And that is not an accident. The lessons from Morse theory of manifolds teach us that if we concentrate index 1 saddle points at a certain level of a random energy function or a generic energy function in the Morse sense, we should expect to see percolation of level sets at that level. And so this is something that we can actually, you know, very concrete. It's very difficult to say, okay, I want to find a percolating level set using theory. This is not an easy thing to write down a problem for. But you can say, I want to find all of the index 1 saddles and look for a place where they're concentrated, right? That's very tractable. And so this is going to motivate us to study stationary points, you know, saddles, minima, maxima, looking for these places where, because of concentration of low index saddles, index 1 saddles, we expect the landscape to shatter into pieces and make it difficult to go below. Yes? Sorry, in this example? Ah, sure. And what do you, when you say no fluctuations, you mean like if you have a finite temperature? Or quantum. I can't speak to quantum, but typically, I mean, you can try, I mean, having a finite fluctuations of temperature is basically annealing, right? And even when you try to do annealing with something like this, I mean, it's true that the overwhelming probability of the first point that you find when you descend in this landscape will be one of these, a very shallow point under this level, let's say. But because the vast majority, the exponential majority in n, in the dimension of space, of points are these very shallow points very close to this level, even trying to do some hopping around and looking for a deeper place won't help you very much in the large n limit. So what can we learn from the statistics of stationary points? We'll go back to my nice cartoon landscape, where we're going to see the types of things that we can fix and quantify about landscapes in general. So first, we have to define a height. This is minus the energy, typically, for physicists. But we can count all of the maxima, say, at a certain height, and compare them with the maxima at different heights, and then say things like, okay, well, there are more at maybe the lower height, but at the higher points, they're clustered together with structure that is different from at the lower point. We can also talk about the type of stationary point. We can say, well, you know, I have maxima that are very stable. They have a stiffness associated with them. We have less stable ones. We have marginally stable ones, which are asymptotically flat. And these will be quite important in this analysis, in high dimensions. And we have saddle points, of course. And in 2 dimensions, there's only one type of saddle point. In n dimensions, you have n types of saddle points, so, or n minus 1. And so you have the saddles galore to try to fix and study different properties of. Yes?
Sorry, I don't get well the definition of stability. I would say that what you call less stable should be more stable because the gradient is smaller and the vice versa. What you call very stable, look, that if I move a little bit, let's say the ball will go down very fast and vice versa. So I would
think about right now we have minus the energy as up. And so you're thinking about trying to maximize in this example. Yeah.
Ah, okay, I see.
It's a
I
bit
see.
of, I've flipped things over from the normal physics picture because
Okay, fine.
trying to highlight the little valleys is much
Okay.
more difficult.
And I guess, let's say, the percolation threshold is essentially the point where the numerical algorithms start to fail, because it's when they got stuck in the landscape and then...
Sure, sure.
Yeah, okay.
This is what we expect. So with this sort of tools, if we have this tool set, if we were able to count or describe the statistics of stationary points by their height and by their type, we can now begin to quantify the difference between a landscape like this, whose highest peaks are stable maxima with a certain sort of clustering configuration, and a landscape like this, whose highest peaks are typically seem to be marginal or nearly marginal, very flat, with a different clustering configuration. So how do we actually count these points and specify their type and height? Well, there's a nice mathematical tool for this for theory, let's say, which is the so-called Katz-Rice method. Now, the idea is to simply evaluate an integral. And typically, we'll evaluate this integral using techniques from mean field theory. But the integral is quite straightforward in terms of what it means in counting stationary points. It's over a measure that has two pieces. The first piece contains a delta function with its Jacobian. And this piece will count 1 every time it sees the gradient is 0, a stationary point. So we're just simply counting the stationary points. And the second piece specifies that we want to count points that have interesting properties, that have a certain energy, a height in the landscape, and this thing I call stability, which I'll define in detail on the next slide. But you basically can think of this mu stability as fixing the type of stationary point, as I described. And with these tools, okay, this will get, if we were able to evaluate this integral for a specific function h, we would get a count of the stationary points that have these properties. But we want the average over the family of functions, drawn from a certain distribution that we described in our model. And so we want to average this value. And there's two ways to do it. The good way to do it, because this number of stationary points is very large, exponential in the size of the system, the good way to make the average, to make sure that what we find is a typical count for systems that we are likely to encounter by drawing from the distribution of functions, we should take the average of the logarithm of this number. And this is the so-called complexity, sigma. This is the, when complexity is 0, we are vanishingly likely to find stationary points of that type. And this is to be contrasted with the so-called annealed average, which takes the logarithm of the average. And this is easier to compute in most circumstances, but it can be biased by rare, unrepresentative samples, and can mislead you. So this is our tool set. This is the basic way that in these mean field models you can make counts and specify types of stationary points. So how do we actually specify types of stationary points?
Sorry, I have a question about this.
Yes.
Sorry, the delta function is a real delta function. It's infinite if it's non-zero. It's the usual delta function.
Usual delta function.
So n is going to be singular exactly when you find a stationary point at that e, but it's going to be...
Yeah. The delta functions of e and mu are a little bit of a notational courtesy. They are effectively regularized by the fact we're taking an average over an ensemble. But if we were interested in actually doing this right for a specific model, typically what you would do is you would say, I want to count, I would replace the delta function with a theta, and I would count a cumulative number, and I take the derivative and get this.
That's what I thought. Okay, good, thank you.
Yeah. It's a little bit of a lie, but it is regularized nicely by the fact we're taking the average. You can do other regularizations if you like to, take a limit of a Gaussian or something.
Just to make a connection with the notion of quench and anneal that I'm used to.
Yeah.
Here, passing from quench to annealed and vice versa is like promoting a disorder to being a dynamical field.
Yes, precisely.
Okay. What is this? What do you promote? The ensemble average become essentially a dynamical field.
Yes, exactly. I mean, I've kind of hidden the quench, the variables involved in the quench disorder by defining my model as with this covariance. But I told you that to make a specific instantation of these h's, you would take a tensor with p components and fill them with IID random variables.
Okay.
And so these tensors, which are basically just the random couplings between the different axes of the sphere, are precisely what would be promoted to dynamical degrees of freedom in this annealed picture.
Is there a reason, I mean, I'm not from the field,
Yeah.
that N is playing such an important role? I mean, is there a reason you're trying to do all dimensions at once, or?
Well, we're trying to do the limit of very large N.
That's
We're
what I
going to
thought
do
you
mean
were
field
going to.
theory.
Okay, you haven't mentioned it yet. Okay.
Sorry, yes, we're doing, this is the way that we actually will evaluate this, and I'll, in several slides, come back to it, at least qualitatively, but in my chalkboard talk, it'll be in great detail, is using a saddle point calculation. And so we want to take N large in the end and have everything described as an integral of N times an effective action. So this mu, this thing which I claimed could classify the type of stationary point, how does it do it? Well, these models have another way, even not just the pure models, all of the spherical spin glasses have another way in which they're not very generic. And that is that the Hessian of stationary points at every single stationary point has a spectral form, a spectral density with the exact same limiting form, which is the Wigner semicircle, but shifted by different constants. And so by fixing this stability, mu, which is the trace of the Hessian, we fix the shift. And because every single one of the stationary points in the large N limit will have a spectral density with the same width, this width, what I call mu-m, a so-called marginal stability, this effectively fixes the type of stationary point. So if we have this mu, the stability, less than this mu-m value, then we have saddle points of different index because we have some number on average of downward directions. If it's greater than the marginal stability, then we have minima of different stiffness because we only have positive eigenvalues in the spectrum. And if it's exactly the same as the marginal stability, then we have a pseudo-gap in the spectrum of stationary points, and you have so-called marginal minima with very flat asymptotic directions. Now, in high dimensions, in mean field theory, index 1 saddles and these marginal minima are not distinguished for the largest order in N calculation. And so in fact, when we want to look for places where we have the percolation of the landscape, what I told you in that nice cartoon in 2 dimensions, we should look for the concentration of low index saddles. Really, what we'll be looking for in practice are concentrations of marginal minima, right? Where this spectral density goes from having an extensive number of downward directions, saddles of extensive index, to having none. This is the transition point. This is where we expect to see this percolation. F. Oh, F was the covariance function I defined on the slide introducing the model. So it's the function I choose, for instance, in the pure p-spin models. Actually, the pure p-spin models, F is q to the pth power, for instance. And in the mixed, it's a sum of 2 different things. But it could be any function you like. I mean, it's just defining the covariance. It has to have positive Taylor coefficients to be a good covariance. So in fact, if we return now to these pure p-spin models which have this interesting dynamical behavior, we can use this analysis, the annealed version, this is a very old work, and see what it tells us. And the answer is interesting. So there's this plot here, there's going to be a lot of plots like this. The x-axis is a function of energy, and the y-axis is a function of stability. And in these models, there's another very non-generic thing. The pure models, at every energy, there's only one type of stationary point found. There's a one-to-one mapping back and forth between energy and stability. And so if you're lower than the marginal complexity mu-m, in the blue part of the line, you find saddle points of a certain average extensive index. If you're above it on the green part of the line, you find minima with a certain stiffness. And if you're the only place in the entire spectrum of energies, the limit of large N, where you find marginal minima, is this energy, the threshold energy, where this line crosses the marginal stability. And this is exactly the picture that I motivated earlier, right? We have literally in the large N limit, every marginal minimum, all these low index saddles concentrated at the same energy, which in fact happens to be the very energy which you find no matter what sort of protocol you use, as long as you go low enough in temperature. And so this is the kind of qualitative picture of what we have here. You're descending the landscape, say, gradient descent or annealing, and you're encountering lots of saddles as you go down in energy, but all those saddles have the same form, the same number of downward directions. And eventually, you stop.
Jaron, let me ask you a question, sorry, before we go in. Is there a reason a priori to assume that this density of states, as you defined it, is self-averaging?
Yes. I mean, so this has been worked on actually. Now, The old work on this was done by physicists. The new work on this from 2012 here is done by mathematicians who in fact have proven that all properties of the Hessian concentrate very, very rapidly on their large N values. And so the properties of the Hessian, like this, the fact that the spectral density has a certain form in these models is not an open question. It's well established.
So it's not, you don't have to worry about the singular continuous spectrum and things of that sort?
No, I don't think so.
Why is that? I mean, you can think of this Hessian as some kind of Schrödinger operator or something of that sort.
A Schrödinger operator. I'm afraid I don't know how to think of it as a Schrödinger operator.
Well, it's some differential equation, some operator in some high-dimensional space. And
I mean, I think of the Hessian as the second derivative of the energy. And this,
yes,
you can write down as, sorry, you can establish as a, sorry.
It's an operator that acts on some space of functions. You use that to compute the determinant, after all.
Yeah. It belongs to the GOE class.
Yes, I can see that in this case. That's why you have a Wigner distribution. But
and what you're trying to ask why it's not, the conditioning on stationary points in energy isn't changing the form of the spectral density?
Yes.
Yes. So in this case, there's two reasons.
There's a famous problem in physics called the Anderson localization.
Yes.
It does happen.
So in this problem, because we're dealing with Gaussian random functions, actually the Hessian is statistically independent in the large N limit from the energy and the gradient. And so in fact, it's the spectral form of any point on the sphere, not just stationary points, takes the GOE form with this shift. And it's quite safe. I mean, I'm not an expert in random matrix theory, but I read the papers from mathematicians to then reassure myself that what I've done is all right.
Okay, thank you.
All right, so this is the qualitative picture that kind of arises from the complexity that I showed you, which is that you encounter one type of saddle point as you descend in the landscape at each level in energy, until eventually you stop finding downward directions. You find marginal minima, you know, they're flat. Maybe it takes you a while to actually find one because there's not a really decisive gradient, but you become stuck. And so this is a nice explanation of what we saw in the dynamics. Now, you might hope to export this intuition to other things. For instance, this is a similar plot of index density versus energy in actual numeric Leonard-Jones liquids. And you can see there's kind of linear dependence of the index density on the potential energy density, but it's not quite sharp. You know, there's not a one-to-one correspondence. There's some breadth here. I'm not sure how it goes in large N. Yes. This is not an important thing, but it's a motivating example if you have a... So it's natural to ask, okay, the fact that we had this one-to-one correspondence between type of stationary point and energy was very nice. It let us quite not rigorously, but it let us quite surely say that we'll expect only to find a certain kind of stationary point at a certain level. Yes?
Sorry, I need a little bit more. I mean, the broaden, the horizontal broaden means, can you explain a little bit compared to the other one, what is the...
So here, if I fix the energy to a certain value,
right,
I have a unique type of saddle point given by this stability.
For a given mu, let's say.
For a given mu,
I find only,
Mu, for saddle points, you can write down the index density as a function of mu, you know, there's a way to do it. And so here, the way I'm showing this basically to motivate showing this, which is the same complexity contour plot, now for a mixed model that has a 3+4 interaction, but now there's not a one-to-one correspondence. If I take a slice of energy, I find a range of stabilities of different kinds of saddle points and minima, sometimes a coexistence at a given energy.
Okay.
And now it's not so natural to say, I'm very sure that this energy is the important one, because you find exponentially many marginal minima at a range of energies, all the way along this yellow line.
Okay.
Now, that's basically the point of that slide. So in fact, here we go. If we look at the annealed complexity of any mixed model you like, you take another term, you leave this very non-generic space of the pure p-spin models, and you find that this complexity broadens. Now there's not a one-to-one correspondence between energy and stability. we can still draw a nice blue and green line showing the place where at each energy the exponential majority of stationary points are, right? But it's no longer true that they're the only ones. There's a breadth. So an old idea, so actually here's the qualitative picture of this now. There's a mixture at each level. You find a mixture. Now an old idea is that it shouldn't change the analysis so much. We have, after all, this complexity is e to the n times the complexity. So if there's a little more, if the complexity is slightly higher for a certain kind of saddle point or a certain kind of minima at a given energy, that means that they are exponentially more numerous. They are the majority by a huge amount in the large n limit. And so you might expect a sort of majority rule, that the threshold should correspond with where the line of the dominant population becomes marginal. And so this is a very old idea, and it was basically taken as assumption in the field for quite a while.
So how you define complexity in this context?
Sorry, it was what I defined on the slide with the integral function. It's the 1 over n times the average of the logarithm of the number of points.
That will be the complexity?
That's the complexity, yes.
Okay. Is the average free energy, is the complexity, in other words, something like that? Okay.
It's the, yeah, sort of. So this is an expectation you might have, given some intuition about these models. But in fact, and here's the intuition again, which is that, even in this plot, this percolating thing, which basically does percolate on this nice two-dimensional plot, it doesn't contain every saddle point, right? There's some that are outside. But in fact, recent work by a colleague of mine has shown this is absolutely not the case. If you take one of these models and you do the dynamical mean field theory with quenches starting from different temperatures, you find that the end point of the quench goes to different energies. And in fact, doesn't even seem to be the case that a quench from infinite temperature goes to this threshold. It seems to go above. And so a natural question then is, how do we resolve this problem? So this is what I just said. Different procedures reach different energies. Neither kind of bound on the energies you reach by different procedures appears to correspond with the traditional idea of the threshold being this majority point. And so this, and here's this picture now of this model I showed you, this 3+4 model. There's this red line here, basically shows you the range of energies of types. You always find marginal minima. You always find these types of stationary points, which we expect are the things which shatter the landscape. But the energy at which you find them, it varies. If you quench from infinite temperature, you go a little above the threshold. If you quench from a very low point near the dynamical transition, you go below the threshold by quite a bit.
If I understand correctly, it looks that in this scenario, you have your total landscape take a form of, with various, let's say, basin of attractions, such that depending where you start, you end up in a, it's correct? The intuition?
Yeah.
Okay.
So I mean, you're kind of, at the end, part of my, the future research I hope to motivate is that we need to study basins of attraction more carefully. Right?
I see. Okay.
And I think the picture of majority rule, it's basically a picture in which you kind of assume an equivalence between basins of attraction. Okay. And you say, well, if each is attached to a stationary point, then the basins which will cover most of space will be the ones covering the majority stationary point. But this is not true, in fact, in practice.
But let's see. Why can you come probably one slide back? Here? Probably two. Okay, here. Let's say the plot on the right doesn't disprove the presence of basin of let's say that all the basin of attractions are equivalent, right? They could be equivalent, but still, depending where you start, you end up in a single basin of attraction rather than the others, right?
So in these models, these are initial studies done by my colleague. It took a lot of numeric work and fitting in things to convince from this data, in fact, that these are going to different energy levels. But when you study, as the same colleague did last year, when you study models with a wider separation between the two terms in the covariance, so like 3 + 6, 3 + 8, these are less pure-like in a sense, right?
Right.
They're more different from a single homogeneous polynomial. Sure. And in these, it's very clear that the asymptotic energies you go to are nowhere near the threshold energy and change a lot by temperature.
Okay.
I'm just not showing these because this is a slide that I took before that paper was published.
Okay. I mean, I would say that more, I would say the majority rule is more like to say that there is, if I understand correctly, there is one basin of attraction that is largely dominant with respect to the others.
No, not at all, not at all. If you take the same instantation of the disorder and you start from different initial conditions and do the same algorithm, you'll find exponentially many different marginal minima at the threshold energy in the pure models. It's not one you're hitting, and you make a new model, you hit its one, you get a new model, you hit its one. No. In each specific model, there are, a complexity. There are exponentially many marginal minima at that energy in a specific model, in a specific instantation of the disorder.
Okay.
So it's not one basin that's huge that you're falling into. You're falling into one of the extremely many basins belonging to minima of this class.
I see.
Yeah, that's an important thing. Thank you for asking this question.
Okay, thanks.
Okay, so, yes. So this should motivate us to study these problems a little more carefully. Because clearly, we're not able to explain things with just the annealed complexity. And the annealed complexity can be kind of not great for us for two reasons. The first reason is it can be misleading. It can give us results that are not typical of samples you would pull from the set of functions. It also like throws away some information, which is nice. Annealed, basically, for technical reasons, assumes that the stationary points are uncorrelated on the configuration space. But, I mean, I told you in my nice little pictures of mountains that measuring clustering structure, how they group together in space, is interesting and intuitively should provide some sort of new information about these models. And that, in fact, comes, not for free, it comes at the cost of doing the quench calculation, but it falls out of the quench calculation in the form of the order parameters involved. And so by moving to a quenched version of the complexity, we both get the more assurance about that what we've plotted here is actually going to be true for one of the models that we pull out of this distribution and run an algorithm on, and we get, alongside of it, these clustering order parameters. And so in order to move to quenched descriptions, I'm going to first have to do a quick qualitative crash course in replica symmetry breaking and what it qualitatively entails. So in my opinion, it's a bit of a misnomer because statistically, so here imagine all these stationary points at the lowest level, right? Statistically, they're indistinguishable. If you find yourself in one, they're not asymmetric from the others. But there are different ways to pick two of them. You can pick two points from the same little basin, right? You can pick two of the same point, basically. But you could also pick 2 points from different basins, right? And these will have a characteristic separation, right? Which is bounded because they belong to some finite basin, some low canyon in the landscape, but nonetheless, it's 2 different stationary points. Or you could pick 2 stationary points from completely different canyons in the landscape. And this, when you have kind of holes or canyons in the landscape, which maybe have sub-canyons, which maybe have sub-canyons, this leads to a hierarchical structure in the typical distance or typical overlap between pairs of stationary points that you draw from the landscape with certain properties. So, when we find that stationary points with certain properties like energy and stability are characterized by certain different types of characteristic overlaps, that's telling us that there's clustering involved, right? That finding a certain stationary point in the landscape means that we're likely to find some around it. We're much more likely to find some around it than we would in a case where they're just uncorrelated. So what does it look like to try to do a quench calculation? Many of the details that are behind this slide I will be sharing in my Blackboard talk on Wednesday, but there are many manipulations that one does to this first integral that I showed you on the slide defining the complexity. And when you finish all of those painful calculations, you get something which in mean field theory we really like, which is an integral over several order parameters, 3 matrices that are 3 matrix order parameters and some scalars of an effective action, right? This effective action has some complex form based on the various order parameters, and the name of the game with an integral like this with an n out front in front of the effective action is to try to find this complexity by evaluating this effective action at a stationary point of its order parameters. Now, this is easier said than done. So there's two big complications here. The first is obvious. There's a lot of order parameters, right? Even if we assume typical Parisi structure, hierarchical things for these matrices, that's a lot of order parameters inside each one, and it's a bit of a mess. Now, the second thing, which makes it even more difficult, and actually intractable to just sort of insert an ansatz and look for saddle points, is that when you do this sort of game with free energy, you typically have a variational problem, because free energy, mean field free energies, bound the real free energy from one side. In this problem, we didn't start with a nice sum of exponentials, which of course we know, okay, sums of exponentials have very nice properties. They're all positive things. We started from an integral over delta functions. And this has no variational properties whatsoever. And the stationary points, which will maximize this integral, are typically real saddles, unstable. And if you just start your saddle finder from some random place in configuration space of these order parameters, it will almost always just fly to infinity or negative infinity, which is not good if you actually want to characterize this thing. And so the way that we're going to try to get around this is to pick a point where we know something about the solution already. And if we can solve the problem at one point and get the order parameters associated with the solution there, we can continue analytically, with our new numeric root solver, take little steps and resolve nearby the known solution to actually find the properties of the non-trivial phase of the complexity in the rest of the configuration. So the first place I'm going to talk about making this correspondence is at the highest peaks of the landscape, which are going to be in fact, the lowest parts of the landscape in our physics picture, the ground states. Now, there is a lot like a free energy in the complexity, and in fact, in the limit of taking the energy to the ground state energy, there is a formal correspondence between the complexity and the limit of temperature to 0 of the free energy. And this should be somewhat intuitive. I mean, the limit of temperature to 0 of the free energy literally becomes the ground state energy. But this correspondence has more than just a schematic form. There's a literal mapping between the equilibrium order parameter in these models and the order parameters we get trying to do the complexity calculation. And this, okay, the intuition for the relationship between the form, so if you have a certain amount of hierarchy in the structure of equilibrium, you have one less hierarchy in the structure of your complexity. The intuition for this is that, okay, you imagine you're looking for the ground states, which have some sort of distribution on the space. And if you take a Boltzmann distribution from the same space and start to lower the temperature, they begin to concentrate on the ground states, right? But whereas in the complexity calculation, a stationary point and another in the same stationary point have overlap 1. There's only one stationary point at each stationary point. At low but not 0 temperatures, there's a little width associated with the Boltzmann weight as it concentrates around a given stationary point. And it's the vanishing of this width which leads to this correspondence here. And so the strategy is going to be the following. We're going to exploit this correspondence using equilibrium, which has fewer order parameters, of variational problems. We can use minimizers instead of horrible saddle point finders to find the order parameter values at the ground state in models that, of course, will have a non-trivial ground state. We better hope that's true. And then we can sweep the rest of space and see where the complexity should be changed in a quenched picture. So here's an example of this. So with Jorge Kirchon, who is my postdoc advisor in Paris, we made this happen on 2 different example models. One whose equilibrium was 2 RSB-like, so okay, 1 RSB, the simplest form in the complexity, and one with a so-called full RSB, a continuous hierarchy of canyon within canyons. And so in this case, this is the example of the 2 RSB on the contours here. You can see the annealed complexity, which I'm showing you, gives a bad answer for the ground state. Because it predicts the ground state energy, which is the farthest, for you guys, left point. It predicts that it should be among saddle points, points whose stability is less than the marginal stability. But this is impossible. You can't have downward directions at the ground state. When you make this correspondence and you sweep your analytic continuation, you find a region, some types of stationary points in energy and stability, where the annealed complexity is corrected bit by a new phase. I've drawn here this transition line in red. And if we zoom in on the ground state energy, we see indeed, just barely, it now exists among stable minima. And we have a good prediction for this point. I told you this kind of naive threshold where the population of marginal minima is the dominant population of stationary points. And so a question here is what about the dynamics? Is there anything interesting to say from this? And there already is one very interesting thing to say, which is that we can say with very high certainty that the threshold in this case is completely irrelevant to dynamics. And the reason for that is that our mathematician friends have proven, as I told you about the simple models, they also proved the algorithmic limits for these models, not just in a annealed case. They proved them in a rigorous way. And the algorithmic limit that they proved, the lowest point that any reasonable algorithm can go below in polynomial time, is above the threshold, which means that you're never going to encounter it if you only have polynomial time. And so that's one lesson from this calculation. We also did the calculation for the full RSB case, which structurally is a little bit less interesting. In full RSB, the ground state corresponds with the threshold, corresponds with the marginal state. Full RSB you can think of as having very flat bottoms at the bottom of the landscape, the ground state. But we were able to do this transition line analytically, which was a very nice thing. So this is interesting. It shows us that in these models that have very non-trivial RSB, for instance, in this previous model, that our intuitions are quite wrong, definitely, when it comes to this threshold energy structure. But we weren't interested in these models with weird RSB. We were interested in a model, this 3+4 model, this original motivating thing that my colleagues studied initially, which doesn't have any non-trivial ground state. And so the question next is, how do we study the non-trivial correlations between saddles, which are like little mountain passes? My cute pictures, you know? So you know, this is our model, our 3+4 model, the picture I showed you, which already has this property that the threshold isn't the attractor of dynamics at either bound, and there's a range of energies you approach. But we notice from our quenched calculations that the range of points, of stationary points that have non-trivial replica symmetry breaking structure, non-trivial clustering, physically, that really corresponds to correlations, clustering correlations among the stationary points. These are mostly among saddle points, right? Below the yellow line are all saddle points. And you see you have a little bit of minima way up at the top, described by some sort of clustering. But then you have this big stripe of saddle points, of these very high index saddle points down the side. And so the question is, could they exist here? And how would we find them if we don't have the ground state correspondence, right? Because the ground state here is trivial from the respect of the structure of stationary points. So the answer comes actually from a lesson from the quenched calculation we did starting from the ground state. So for instance, I'm going to talk about a 1 RSB, right? So in 1 RSB, there's 2 order parameters associated. There's a Q, which tells you about how tightly the things are clustered together. And there's another order parameter, X, so-called Parisi order parameter, or Parisi parameter, which tells you basically the fraction of unclustered pairs. How prevalent is the clustering among saddle points of that type. Now, on the transition line between symmetry and symmetry breaking, you find always that this fraction is 1. Basically, you're seeing no correlations, no clustering, and then you start to see a tiny bit appear with some clustering structure that just sort of always has some value randomly between 0 and 1. So it's difficult to look for this transition if you don't know the value of the order parameters at where it is. However, at the endpoint of this transition, where it meets the 0 complexity line, it appears from our quenched calculation that both order parameters are 1. So we know both of their values. We know all to look for this transition, all we have to do is look at the stability of our effective action, which, okay, it's not going to be a minimum or a maximum. Again, I told you this, these are real saddle points. But still, the stability will change. An eigenvalue will flip if we go over a place where a new solution branches off. And so we can search the 0 complexity line of the annealed solution of any model for a place where the 1 RSB effective action has such a change in stability. And this is what I did in a recent paper. I was able to do analytically for any of these functions which characterize the covariance of the model, make a formula which tells you, if you evaluate this formula, if it's greater than 0, then you have transition endpoints, and therefore you should expect to find some clustering structure among saddle points in the landscape. Now, the surprising thing, so this plot here is showing the sort of phase diagram as a function of model parameters. So for 3 plus S models, that's a 3 and an S, so 4, 5, 6, what you like, with a variable weight between the two terms, you can see that there's a broad, in the blue section, there's a broad range of models which have an RSB complexity, which is much broader than the range of models in the green that have a non-trivial ground state from the complexity perspective. And it's even broader than the class of models which is permitted by some equilibrium properties from having replica symmetry breaking, more than one RSB, so non-trivial from the respect of the states, in equilibrium at all. And so this is interesting. You're finding models, lots of models, which will never have any interesting structure beyond completely uncorrelated states in equilibrium, but which have some saddle points high in the landscape that nonetheless are clustered together. And here's an example of this. This is a model from this class which is forbidden from having any sort of interesting equilibrium. And as you can see, you find a range of energies where the very thin sliver of the highest index saddle points exhibit some sort of clustering structure. Unfortunately, for our overarching questions of dynamics, this doesn't help us answer anything because it doesn't appear that these, I mean, you can imagine in out of equilibrium scenarios, these could be important in certain settings or something. But in general, it doesn't seem like the onset of the saddle points clustering has anything to do with the specific energies where we see dynamics go. And moreover, if we go back to this plot, this phase diagram I showed you, if you look at S equals 4, which is the 3 plus 4 model, what we were motivated by, indeed, no combination of a q cubed and a q to the 4th term results in clustering among saddles in this model. And so it may have influence in these models, in the dynamics, that's open, but it certainly is not going to explain this range of energies you find in the 3 plus 4. But at least now we know exactly where the annealed calculation is going wrong in these models and how to compute exactly what it should tell you if you're careful. So moving on, how else might we try to get at dynamical behavior? Well, now we're going to talk about planes. We're going to focus back on the marginal minima, the things which we are, from empirical evidence, are the endpoints of a variety of algorithms, both physically inspired ones and fancy ones, which are leave the configuration space. So the motivation here is you imagine, okay, here's a nice picture. I think this is near Milan. And you imagine you're down here in the plains and you want to get to the top of the Alps. It's an optimization problem, but it's cloudy, as it usually is in Milan, and so you can't just look and go. You have to use local information only. You look at the small gradient nearby, you follow it. This will take you on a long, meandering, slow path on very slightly rising hills, which doesn't necessarily correlate well with the direction of the Alps, and maybe you find yourself at the top of some very shallow hill at the end. Now, this is the qualitative picture of aging dynamics in these disordered systems. The idea is that you descend quickly in the parts of the landscape which have all these downward directions and saddle points. When you meet a whole bunch of marginal minima, these very flat things with little flat barriers between them, the gradient becomes very indecisive, and the result doesn't correlate well with very low points. And this stage on which this sort of thing happens is known as marginal manifold. It's this idea that when you have these little marginal minima in the landscape, because they have flat directions, you can insert lots of little marginal minima arbitrarily close together with little tiny sub-extensive barriers between them because the directions are flat, right? Small variations in the random energy function lead to the insertion of lots of little marginal minima very close together. And this is thought to be very important for the qualitative picture of aging. And so if we go back to this picture, which I've highlighted the marginal minima which attract quench dynamics from different temperatures, one might imagine, one might hope, that the structure of the relationship between marginal minima, this marginal manifold, how close they tend to be together, this sort of thing, that this might be different between those which attract aging dynamics and those which do not. That's a natural idea, perhaps. So I set out to study this last year. And the way that one proceeds is the so-called two-point complexity. You take, the complexity, so the average of the log of the number of stationary points of a certain type energy stability, conditioned on the fact that a second stationary point, with its own properties, exists at a certain distance away, a certain overlap with the one that we're counting. So, for instance, you imagine, for this motivation I've given you, you want to fix a marginal minimum with a certain energy, and you want to ask the question, conditioned on the fact that a second marginal minimum is nearby, as a function of distance or something, what's the complexity of the ones that I'm counting? And this is hopefully going to tell us something about the structure of these marginal manifolds. Now, unfortunately, it doesn't end up telling us that there is a difference between the ones I highlighted in red and the other ones. In fact, this calculation, very disappointingly, only reinforced the geometric importance of this threshold, this stupid threshold, which doesn't actually attract the dynamics in these models. So what I found when I did this calculation was that when you look at the threshold energy, you find exactly what you expect, which is that the complexity, the range of energies nearby where you find marginal minima, some overlap, you go all the way to 1. You find marginal minima at arbitrarily close distance together. This is the picture of the marginal manifold. Very, very close together minima, very small barriers between them as a result. But both below and above the threshold energy, I find an extensive gap between marginal minima and neighboring marginal minima, which is quite unexpected. It's even difficult to think about geometrically how this happens. But this calculation produces this result, and it's interesting. I think it makes us have to really reevaluate the intuitive heuristic picture of aging dynamics, because this is telling us that we have marginal minima with energies that attract aging dynamics from DMFT and simulations. This is established, which, according to this calculation, are extensively far apart. So don't share this flat plane with many minima around them. Now, they are arbitrarily close to saddle points and things, so there are ways to have large flat regions around them, but nonetheless, these are isolated minima, marginal minima, that are being approached at these levels. I can see Dario is preparing the microphone.
Look a little bit, I don't know if it is any connection, because here it's, but it looks a little bit like presence of level repulsion in chaotic Hamiltonians. Like the two levels, let's say, two minimas, tend to repel to each other. So if they are close in energy, they go far away in space.
This is the thing, though. So when you have stable minima, this absolutely holds. And the intuition is simple. It's that if you have a certain stiffness, right? So the stiffness is telling you basically the local curvature at the minimum. Then in order for the random function to turn this over and produce something else, requires some amount of space,
separation.
Right? That's the intuition for this. But when you have flat minima, when you have marginal minima, where the asymptotic stiffness is 0, then infinitesimal variations of the function should produce little tiny minima nearby. Now, this calculation, because it's a mean field calculation, order n, it doesn't actually distinguish between a single minimum at a point and a sub-extensive number kind of very close to it, right? So in fact, what is probably happening in these below and above scenarios is that you have little tiny groups of marginal minima very sub-extensively close together, right? Because of these little flat perturbations, which nonetheless, by the time you get an extensive distance away, even a very small one, have somehow, left that energy level.
I don't know. Just again, as a blind intuition, I would try to study the statistics of these energy gaps to see if they show a Wigner-Sarmais-like shape, because it looks very similar, at least morally, let's say, to something related to level repulsion. So I don't know. Yeah. Okay. Thanks.
Oh, it's a good idea. Thank you. So I think. Oh yeah. So this is the end of the talk in terms of my recent research, which disappointingly hasn't answered this question about where things go. But I hope it motivates well my proposals for future research, which basically fall Okay, there's more of these, but the big ones fall into two basic camps, one of which is to go beyond spin glasses. So despite our great efforts and failure to discover which marginal minima attract quenches from certain temperatures, what have you, it's pretty well established at this point that marginal minima are the attractors of dynamics for a wide range of algorithms. And so if we can understand where marginal minima are, where they have a finite complexity in a given system, model, problem, what have you, we can effectively, in a fairly algorithmically independent way, bound the outcome of a lot of kinds of dynamics on that system. And so one set of projects that I've been working on is to take these tools, which are very well honed in the field of spin glasses, which basically means Gaussian random fields, and export them into the burgeoning and interesting growing field of inference problems in machine learning, where almost none of the interesting problems are Gaussian in the structure of the function. They're decidedly non-Gaussian. And I have some progress on this, which I'll share on the next slide. The other side of my proposals is to try to get at this problem again of let's say, reduce the problem to a much simpler form. If you do a quench from infinite temperature to zero temperature, which energy level do you end at, right? That's a tractable question we still haven't answered. And with this, the proposal is basically to go beyond complexity. Basically, what I have come to the conclusion from this amount of effort in trying to answer this question, looking at stationary points, pairs of stationary points, even triples, local information won't be enough. Something about the structure of basins is very important to actually get at questions like these. This part of the proposal basically proposes generalizing complexity analysis using tools from DMFT to study higher dimensional objects to get at statistics of basins. So first, beyond spin glasses. So this is probably the simplest non-Gaussian model you could ever think of. It's random nonlinear least squares. You take a whole bunch of spin glass Hamiltonians, which have the same covariance I told you before on the sphere, and you sum the squares of their values, right? And now you want to minimize this function. Well, actually, minimizing this function, it turns out with theory, is a little harder than maximizing it, because the bottom either looks trivial or full RSB-like. So in my preliminary analysis of this model, I've been looking at the nonlinear most squares, maximizing this sum of squares. And taking the tools that are well honed in spin glasses and making certain adjustments and things to try to move them into this field of non-Gaussian landscapes, it's possible, in fact, to compute the complexity of marginal maxima in this case, of these sort of functions. So here, for instance, in this model I've outlined is the spectrum of marginal optima for a certain instantation of this problem, and it has some range. And if I run algorithms, using one of my old advisor's computers, crunching gradient descent over and over again, and message passing over and over again, zooming in because it's easier to see, we can see that, in fact, it's not a very tight bound, but the marginal minima do, in fact, bound the performance of these algorithms quite well, at least in this preliminary data. This is fairly recent work I've been working on. So this is a very silly model. No one usually wants to maximize the sum of squares. But the point is that the basic methods which go into this calculation in more interesting models that are actually used in both theoretical computer science, but actually in practical things as well, like phase retrieval, are amenable to these mean field theory techniques, and using the same methods that I've kind of begun working on in this simpler model should be also amenable to this sort of bounding of the performance using this range of marginal minima. Now, the other side of my proposal has to do with studying basins themselves by generalizing complexity. And as I said earlier, the failure of our study of stationary points, right, we can kind of intuitively understand it as related to the fact that stationary points in these high-dimensional problems, they're not connected to basins that have the nice intuitive structure of low-dimensional problems, that, like this top picture here, where all the basins are basically compact and the same size, roughly. In fact, it's known that in glassy problems, these are, I think, soft spheres or hard spheres, basins of attraction, a slice through a landscape. The basins of attraction are very non-convex. They have a wide range of sizes. And our majority rule intuition, or maybe not intuition, but our majority rule bias is completely invalid. We shouldn't expect it to work. So this motivates the study of statistics of the basins attached to stationary points, but this is difficult to do directly because it basically involves having to integrate DMFT to infinity, which is you can't just do unless you have it exact, which you typically don't. And so this is part of my proposal, which I have less progress on, but I've begun work, is to try to generalize complexity to objects called Morse lines. And what are Morse lines? If you go back to our beautiful landscape here, basin of attraction is clearly the set of all points that flow by gradient descent to a certain minimum. Now, Morse lines are the gradient descent trajectories which connect adjacent stationary points. So here we have Morse lines, very schematically, connecting maxima to a saddle point, and Morse lines connecting saddle point to minima. And the set of Morse lines connected to a certain minima or maxima forms a complex going all the way up of all the indices of saddle point, known as the Morse complex, which, if you start inside, will do the same thing, will bound your basin of attraction. So the idea is that these, unlike the whole basin themselves, these lines will make very small changes in energy in these complex landscapes and move very small distances between nearby stationary points, and therefore be treatable perturbatively in the DMFT. And hopefully we can extract something without actually having to integrate to infinity. And the lessons would be, in this sort of schematic case, that the Morse complexes connected to different minima will have different properties typically, perhaps. And perhaps from this sort of analysis, we could then start to suss out, for instance, which minima have the largest basins attached to them, this sort of question. And so I've begun working on this. I have a DMFT solution in the very, very simplest mean field model, which is usually exactly solvable, so it's not a huge surprise I was able to work with it. I've begun work on perturbatively applying the same approach to other more generic models. And I actually already have numeric tools to try to corroborate these mean field ideas, because in a separate paper on something completely different, these are the complex valued landscapes that were asked about earlier, we developed the tools to find these exact gradient descent trajectories between stationary points. And so this constitutes as part of the proposal, which is to use these sort of statistics of these trajectories to better understand how the basins of attraction in these systems are structured. With that, for those watching on YouTube, this is a job talk, so I have to advertise myself a little bit. These are other research projects, not all related to what I talked about in this talk, that I have ongoing, some with collaborators, some of my own. And with that, I'd like to take any questions, both on the content of the talk, and of course, you can ask about these things as well. Thank you. Of course.
Okay, thank you. All right. Thank you. No, I don't have. I may go to something different, but I mean, the whole problem of finding this minimal in the landscape and all that. I mean, it's also similar to the problem in nonlinear systems, complex systems, and of the so-called Riedel basis. So the thing with the thing with the Riedel basis, I mean, there are a lot of people who have seen them. There is no explanation. There is some sort of an explanation by Grebogi, but the only thing is it counts densities of Riedel basis, and they say that. And I don't know if you have seen something like this. Recently, we came across the Riedel basins in a problem of Isikevich networks. And in looking for an explanation for that, what we saw in many cases, but I don't know if that is correct or not. We just wrote it as a comment in a paper that we wrote, but that's all we had. We couldn't prove it in all cases, is that most of the cases that we searched where there were Riedel basins, there was also singularities in the models. I don't know. I mean, we couldn't prove anything. I mean, no, we couldn't prove. We saw. Sorry?
Can you ask the question, because then we have other people online.
Okay, yeah. So this is. I mean, I wonder if you have looked at that kind of problems. Okay.
I have not, but the field, I mean, so I've done a little bit actually. These so-called non-reciprocal systems aren't Hamiltonian systems with an energy function. They're dynamical systems like you described. Like, for instance, the generalized Lotka-Volterra is very popular these days. There was a very nice paper of a colleague of mine recently doing this sort of complexity analysis for that model. And basically the same tools hold. You have, you know, the fact that the thing we put inside the delta function was a gradient wasn't necessary. You could also put a force field or something. Now, the lessons you can learn from the statistics of, you know, equilibria of nonlinear systems are a little different from those you learn from the statistics of minima. It's difficult to say, okay, well, you know, the type of, you know, attractors or something attached to certain types of things will have different properties, but it's a fledgling field, so perhaps this sort of thing could be established in the future. I don't know.
So let's see if there are any questions online, and then we can go back to the, do any of those people want to ask something?
I have a general question. In a sense, you have studied, you know, it's a complicated, complex problem in a very specific class of systems which have infinite range interactions with various degree of architecture, let me call them. In physics, these things are rarely found. So the question is, how general is this? Where do you see all of this going?
Well, the section of my...
If I have any disorder system, typically there will be some notion of distance. And so I'm not trying to rekindle here the old controversies about replica symmetry making. I don't care about that. But the question is how significant this is for the study of disorder systems. What do we learn from this that is generally applicable?
Well, there's kind of two answers to this question. I mean, first is the classic answer you give when you talk about the applicability of mean field results in general, is that maybe they give you a qualitative understanding which doesn't quantitatively carry to finite dimensions, but gives you something. That's one answer. The second answer is that, I mean, if you look outside physics, there actually are a lot of systems people are very interested in, which are fully connected, disordered systems in some sense, which are these inference models. You know, you take lots of neurons, each of which basically looks like some kind of weird, fully connected, nonlinear thing. You string them together, sometimes not in a fully connected way, but also often in a densely connected way. And you attempt to do gradient descent on this sort of weird function to find, you know, values of the neural network parameters which help you minimize an objective. So in this sense, a lot of the direction, I mean, so that's one example, but also in more physical examples, this is true also in a lot of the application of this field is moving away from glasses and spin glasses precisely because there's not so much quantitative things to discuss. But besides machine learning and inference, there's also the study of things like ecology and the interaction between genes, which of course is extremely structured, is not all-to-all in an even, equally strong interactions, but nonetheless is much more all-to-all-like than a finite-dimensional system. And so there's some hope that the lessons we learn from these sort of models may be more instructive in something like in these fledgling areas of physics, which are not, you know, traditional physical systems, more so than they are, say, to like a three-dimensional spin glass, which honestly I'm very uninterested in studying.
Okay.
Any other questions from the online people?
Yeah, I may ask a question a little bit technical, Jaron. Sorry for that.
Of course, please.
Imagine that you know that when you do dynamic mean field theory, you can choose the initial conditions in different ways. So the typical quench one is you take them random from infinite temperature, but then, you know, as these people have done, Colin and company, they have chosen equilibrium levels and then, you know, let's relax the dynamics from there and things like this. But now that you know a little bit more about the structure of, you know, the landscape of these mixed P-spin models, maybe you can constrain your initial conditions differently. So like, you know, you have these low-lying plateaus or, you know, the regions where you have clustering of your solutions that now you know them better. So have you thought about trying to adapt dynamic mean field theory like that and see what happens with the evolution of those?
I mean,
conditions?
in like a very technical way, this is exactly what I'm doing when I'm trying to do this sort of extension. It's not exactly what you're suggesting. So the extension of going to Morse lines is specifically starting and ending dynamical mean field theory conditioned on the presence of stationary points at certain places in the landscape. But it's not exactly what you're suggesting, because it's not like, I specifically want to avoid solutions which then, go through a whole gradient descent and find a distant place, right? It could be interesting. I haven't thought about this. I've been mostly thinking about these very specifically constrained trajectories, conditioned on the presence of stationary points at the start and end.
Okay, thank you.
Any other questions online?
Yeah, I have a question comment. There are problems which are different and maybe related to this. I don't know if you're familiar with the so-called SYK model.
Indeed, yes. It's Jorge's favorite toy these days.
Okay. So if you take two SYK models, which are essentially problems where you have a large set of Majorana fermions which interact all against all, essentially, so it's a class of problems of this type. And if you imagine that there's some interaction that doesn't have to be pairwise between them, you can try to do a lateral quench, for instance. And you ask, is the system going to thermalize? The states that you discuss look to me like the thermal limit, that the systems that actually do thermalize. But people discover there is a non-commutativity between the quench and the large N limit. That the large N limit, in fact, doesn't quite reach the correct value. And I don't know, this is related to your saturation problem that you are discussing here.
That's interesting. I mean, my own understanding of the SYK, which mostly has come from listening to Jorge but not working directly, is that you don't find glassiness, you find slow asymptotic approach to the lower, ground state.
Yeah, these systems don't have any replica symmetry breaking. They're constructed so.
So actually, one interesting problem.
But they still have a problem of whether or not they thermalize, which is the question of whether there is an extensivity or the entropy, essentially, if you want.
Yeah.
Or the entanglement. In that case, it's the entanglement entropy, the one that matters, okay?
I can't really speak to this, but I have started working a little bit with Jorge on a problem, basically trying to construct SYK-like models that involve fermions that explicitly don't thermalize because they have a spin glass-like order, which at this point I don't think that exists. And we're working basically using these tools because, for instance, if you start with a supersymmetric theory, and you fix the fermion number, you're basically fixing the ground states. I'm not a quantum person, so I'm going to make a lot of weird mistakes in how I describe this. But the states that you expect to find when you thermalize are related to the saddle points. If you fix a certain fermion number, they're related to the most common type of saddle point in the landscape of a certain index. And so the name of the game for making an SYK-like model, a supersymmetric one, that has a non-trivial spin glass order among these states, is to try to get, let's see, if I go back a couple slides, it'll be very nice. Here we go. To try to get this red section over the set of dominant saddle points for not minima, right, over the dominant saddle points. And so we're working a little bit on this, trying to dream up an interesting combination, an interesting covariance function, which would have this property. Now, I think this is more motivational for the black hole theorists who study SYK than it is maybe for the condensed matter theorists who study SYK. But it's an interesting thing we're thinking about. I mean, there are deep connections, of course. I don't know a lot about the quantum scenario, though, so I can't speak too much about the details.
Okay, thank you.
Any other questions online? Okay, questions from here?
Sorry, I just wanted to make sure I understood. One of your figures looked like a diagram of the various phases of the model. You had some lambda in one axis. Yes.
Yes.
Could you just summarize a little bit? So if I'm just
Let me go
doing some measurements, what do I find in the different phases that distinguishes the physics in this plot? So lambda, I understand. S, what was S again?
S is, so the model is a sum of a cubic term and an S-ic term.
Good, good. Yeah, so could you summarize in this figure just
what
is the physics in the different regions?
The easiest one would be the green region. So that's saying that the ground state of the model in equilibrium and also the ground state.
Sorry, I am colorblind. Tell me which one is a green region, please.
The one that is labeled RSB T equals 0.
Okay.
The RSB T equals 0 region is the one which corresponds to a ground state that is non-trivial in the replica symmetry breaking sense. It's 1 RSB, basically.
Mm-hmm.
The non-convex chi, the yellow region, there's this, it's a bad label perhaps, but there's from the equilibrium treatment, very old result from the equilibrium treatment of these models from Crisanti and Summers back in the mid-90s. They showed, because when you do the generic RSB treatment of these models, you can express the whole action as a functional of this function chi, and it turns out that if it's, forget that the chi has equal to something of f, there's a functional of some function chi, and if this f here, this double derivative of f to the -1/2, if this weird function is totally non-convex, totally concave, then you have a full RSB system where the solution to the saddle point equation is equal to this. But if it's totally convex, you have no levels of RSB possible, right? Little regions of concavity in an otherwise convex function will give you the possibility of having levels of RSB beyond 1 RSB. Not guarantee, but possibility. But if it's completely, if this function here is completely convex, then there's no hope of finding any solution in the replica symmetry breaking form better than 1 RSB. So it's basically saying that even, ground state is one thing, but you could imagine, I don't know, like an RSB that comes in and goes out again. Who knows? There's all kinds of crazy stuff out there. And that's impossible in this yellow, outside of this yellow region. Inside the yellow region, it's possible to have different RSB structures at equilibrium at finite temperature. And then finally, the blue region is the region where I showed that there does exist some region of saddle points which at least has a 1 RSB complexity, which means that the clustering structure in the saddle points, in the complexity, 1 RSB is non-trivial in the way I'm describing, because it means the points are clustered. Remember, in equilibrium, you automatically get clustering at finite temperature with completely uncorrelated minima, because when you draw multiple points from the same basin, they have some sort of clustering around them. So that's the structure of this diagram.
But can I just ask, so before the physics was about to which energy do things converge, right?
Yes.
And now you switch language, and now you are describing some replica symmetry breaking patterns or not of the ground states. How do I connect the two? I thought that you would tell me that in these different regions I converge to different energies, or in some region there is universality, in some other there is not.
No,
is it true or no?
Sorry.
That's not the physical picture?
Unfortunately not. I mean, so I told you a lot of the motivation for very carefully studying the quench solution to this problem was to see if the quench solution would correct the annealed one in some way, which did teach us something about this. But in fact, so I mean, you see what happens in this, if you take larger, the less pure-like the model is, so the bigger S is in this 3 plus S, the more non-trivial the set of states which has these properties gets. As you can see, for these kind of pure-like 3 plus 5 sort of things, you get a very thin slice of saddles, which it's possible they influence dynamics. It's not certain, not for every dynamics probably. But I guess the point of this picture was that it's teaching us that we can't hope to describe this with this sort of structure, because the models that we're interested in, one of the models we're interested in, which has non-trivial dynamics, doesn't even have a non-trivial complexity.
Okay.
So it's kind of a null result. I mean, it's, you know, we did a lot of work to find, in fact, that we show, you know, the open question before this work was done was, does this model here have, you know, some non-trivial complexity somewhere? Maybe it's along the line of marginal states. Maybe it's high in the energy landscape. It's really not known, right? And the answer that we came up with was no. It has no region which has non-trivial clustering structure, and therefore clustering structure can't be the explanatory force behind the behavior you see.
Okay.
Not very satisfying.
Okay, I'll ask you more at lunch. I have a Zoom call now, so unfortunately I have to run. Okay, see you later.
I have to go now, but just to understand what happens before, can you go back forward one? Or
Forward one here.
Well, to the one he was asking about, the slide
This
he was
one.
asking about. Yeah, that one. So what happens before, I guess it's S equals 4, or for small lambda? So this white region, that's the...
So the white region is where this weird functional that gives you the heuristic, the result, is less than 0, and there is no point along the 0 complexity line where a 1 RSP solution emerges. And so you don't find this section of saddles. Now, of course, there could be some isolated region of clustering somewhere that doesn't hit the 1 RSP line. That's not ruled out by this calculation. One could try to find it. Of course, a lot of the motivation of these sections was about having a point to start at, which makes it very difficult to find such a region, but it's not ruled out by this sort of thing. But the form that we see existing connected to RSB at the ground state, which basically gives us this stripe along the side, it definitely doesn't exist for the models that are in this white region. So models with very large lambda, but like S equals 10, you don't see it. But also models, all S equals 4 models, you don't see it.
Maybe just a couple of things. One, it's, I mean, it's inspired by one thing that I did in SYK. We found that, for example, in SYK, if you make your model, you make your Hamiltonian not Hermitian, you make it, let's say, PT symmetric, you see that replica symmetry breaking become easier. Let's say we found that, for example, SYK doesn't have any, let's say, dominant solution with replica symmetry, instead become dominant. So I was wondering if, let's say, the complex case might be worth and doable.
Well, sorry, for classical functions with complex values?
Yes.
Oh, we did this. So one of the papers I did with Jorge Kirchhoff, I didn't talk about it at all because it's kind of arcane and not easily motivated by you know, these sort of dynamics, was looking at the structure of stationary points. When you, in our case, we took Hamiltonians that were analytic, so which are holomorphic. So basically unbounded configuration space, because we weren't working on Calabi-Yau manifolds or anything. But we did characterize the distribution of stationary points in those models, and we did this paper that I cited as the place where I have my, my nice numeric method on this slide. Analytic continuation over complex landscapes. Those are, so we have one paper called complex landscapes, which in Jorge and I's opinion is the best name for a paper that we can have. And and then here we have, this problem was looking again at basically decomposing partition functions into these things called Lefsch's thimbles.
Okay, yes.
In the case where you have a lot of Lefsch's thimbles and asking when is it tractable, what sort of lessons can you learn? We have some partial answers, but it was a very, we did a lot of delving into the complex structure here.
I see. Yeah, because our example with SYK was that you can get, let's say, replica symmetry breaking dominant solutions in the large N by going to the PT symmetric case. And the other thing, I mean, I don't know if it is still the case, but at least few years ago was very, let's say, fancy in the quantum computing business, talking about Barenplateau problems and so on. Like, I mean, people wanted to find, let's say, the minimum of a certain cost function, and they found that it's quite common that the landscape become flat. And I was wondering if some of your, have you ever thought about some of your...
Sorry, what are the problems you're talking about?
Barenplateau. The thing is that
Barenplateau.
Barenplateau, yeah. The thing is that, let's say, what you can show is that if, let's say, your circuit, your quantum circuit, is to design, so let's say reproduce the hard measure distribution up to the second moment. The gradient become, let's say, vanishing, let's say, exponentially with the number of qubits. So that makes very hard to optimize any of these problems because the gradient become essentially zero and you don't move anymore. And people are probably still a little bit arguing about how to cure this problem, how to make these optimization algorithms work when in this case. So I was wondering if...
Oh, it sounds interesting. I don't know anything about this problem.
Okay,
so
fine.
I can't
Yeah, we can
comment
chat
on it.
later. Yeah.
No, thanks.
Okay, so I guess people can go to lunch and ask more questions during lunch. So Eduardo and Leticia, no more questions?
Not for now. Maybe on Wednesday, but
We'll
not
meet again
today.
on
So,
Wednesday, I guess.
just let me ask you a question. So Wednesday is going to be at the same time, right?
Yeah, yeah, that's the
Okay,
plan.
I will try to join. I'm not sure because I have to do something. One of my sons take him somewhere. So if I find, get a internet connection where we'll be,
Okay.
I will join. Otherwise,
You're going to a you're going to a May Day demonstration?
no. I'm taking him. He's passing all these concours, so I have to take him to
I'm sorry,
Charles de Gaulle.
I'm joking, Leticia.
No, I know.
Okay, so thanks very much.
Okay.
Thanks, Jaron. Thanks, everybody.
Thank you.
Thank you.
Okay, bye-bye.
Bye bye.
So I need to eat very quickly, but I think I need to eat quickly, so probably you guys should go whenever you want.
I can take care of you.